Hello and welcome to the 10th live stream of our Science Salon series. I'm Danny and I'm one of the science communicators at Kyushu University's Public Relations Initiative, and I will be hosting today's Science Salon. Konnichiwa. 第10回 Science Salon へようこそ。Danny です。九州大学の広報本部の Science Communicator で今日の Science Salon の司会です。So just a brief introduction. In the Science Salon series, we introduce researchers from Kyushu University whose work reflects the university's Vision 2030 to become a university that drives social change with integrative knowledge. So with that, I'd like to introduce today's guest, Doris Arzoumanian. And she is an associate professor here at the Institute of Advanced Study. And she is also affiliated with the Department of Earth and Planetary Sciences in the Faculty of Sciences. So Doris is an astrophysicist, and she studies the fundamental processes underlying the formation of stars. So thank you so much for joining us. It's a pleasure to have you.
Thank you very much for having me.
Yeah. I'm
very happy to be here.
So for our Japanese viewers today, could you give us a very quick self-introduction in Japanese?
Yes, sure. こんにちは、ドリスです。天文学者です。星形成を研究してます。星がどうやって生まれるかを研究してます。よろしくお願いします。
よろしくお願いします。So to kind of start off with, I was wondering, can you explain a little bit about your research background and what you study?
Yes, so I'm interested in understanding how stars form. And so to do that, I use telescopes on the ground or in the space to observe the region in our galaxy where there is a lot of material which is assembling in order to form new stars.
So how did you first become interested in this topic?
Yeah, so I think so I've always been interested in understanding things I see around me and understanding the Earth, life, where I come from, why I am here, why all of us are here. And then later on, I understood that planets form around stars during the formation of stars. And so I started thinking that if I want to understand the origin of life, one way is understanding how the planets are formed, and which means understanding how stars are formed. And so that's why I got interested in these topics.
That makes sense. Yeah, I've heard it say that we are all kind of made of stardust, that stars kind of made everything in the universe.
Yeah, I mean, at the beginning of the universe, after the Big Bang, only hydrogen and helium was there. And so the first generation of stars formed out of only hydrogen. And during the evolution of stars, the hydrogen is fused into heavier elements. And basically all the elements that are in the universe today have been made through the life, evolution, and the death of stars. So we are literally stardust.
Yeah, stardust. So yeah, could you just walk me through, what exactly happens? What is the life of a star? How does it form and how does it die?
Yeah, so actually when we look at the sky at night, we see the stars and we don't see anything between the stars. But actually, there is a lot of material, gas and dust, that fill the space between the stars. So this is the interstellar medium. And this material assembles into dense clouds. And the densest region of these clouds, they collapse to form new stars. And so the lifetime of a star depends on the mass of the star. So low mass stars like the sun, they will live long time, and then during their evolution, they will fuse the hydrogen. So that's why the stars are bright. And after they completed fusing all the hydrogen, they will continue fusing the helium will, in nuclear reaction, the helium will form heavier atoms, carbon and oxygen. Heavier stars, more massive stars compared to the sun, they will evolve, they will live faster because they are much more massive. And then they will burn their hydrogen very fast, and then they will be able to form much more heavier elements. And at the end of their life, they will explode in supernova, and then they will eject all this material that they have formed into the interstellar medium. And so the interstellar medium will be enriched with heavier elements, and then this material will mix again, and then will form dense clouds, and then these dense clouds will be assembled into denser pocket of gas and dust that will collapse to form new stars. And that's the cycle of the interstellar medium.
So when we look at the sky and the stars, they're all kinds of very different ages. They exist in multiple different generations.
There are different ages and there are different kinds, different masses. So the sun is one of the most common stars. Most of the stars in the universe are like the sun. And then there are lower mass stars, and then there are stars which are much more massive and bigger than the sun. And then there are multiple events of star formation, and the different stars live different lifetimes. And so then when we look at the sky, depending on the lifetime of the star, the color of the star also changes during their evolution.
I see.
And so this is one of the important questions in the star formation study, is what defines the mass of a star? Why most of the stars are like the sun, but why they are also much more massive stars, and why they are less massive stars? So this is one of the important questions in star formation study.
I see. And is this a specific area that you're interested in?
Yes, so I am interested in understanding the process of star formation, and understanding the process of star formation will help us understand this particular question of the mass of the stars. And as I said, the mass of the star defines the lifetime and also defines how the star affects the interstellar medium around the star, and then eventually affect the evolution of the universe. So the most massive stars are very important for the enrichment, the chemical enrichment of the interstellar medium, and then during their, at the end of their death, when they explode in supernova, they also inject a lot of energy, turbulent energy, kinetic energy, which is very important for the evolution of galaxies. While stars like the sun, they host planets. So planets form during the formation of stars. And so if we want to understand how planets form, we have to understand how stars like the sun form. And so, I am interested in understanding the full process of star formation.
The full picture. One thing I'm curious about is, obviously, these processes occur on time scales that are completely unimaginable to us, like billions and billions of years, right? So how do you study things on such long time scale? How can you be sure of what you're theorizing?
Yeah, of course. I mean, we can, the star formation process can take a few million years.
Oh, relatively quick.
The formation of the clouds is longer, and then the lifetime of stars is much, much longer. And so, of course, we cannot observe this for millions of years. But what we can do is to observe different regions at different evolutionary stages. And then we can analyze the properties of the different regions at different evolutionary stages, and then we can put everything back together to create the history, understand the history. So this is from the observational point of view. But then, in order to interpret the observation, we use theoretical models, and we use numerical simulations. And then with these theoretical model and numerical simulations, we can track the evolution and then compare with the observation and try to put numbers on these things that we observe. But actually the time scales is a very important topic and still very much debated. Is star formation a fast process? We have the clouds, does it collapse and form quickly a star, or does it take long time to form a star? And so there are a few theories, and then we are working on that to try to understand the time scale of star formation. And this is, there has a lot of points where it's important, but in particular is because during the formation process of stars, in the dense gas clouds, there are complex organic molecules that are formed. And then, so this is a part of astrochemistry. And in order to form this kind of complex organic molecules, you need time. I mean, the chemical reaction takes time. So depending on how fast the collapse takes place, you can form or not this kind of molecules. So that's why also, understanding the time scale is important to understand the evolution of matter.
I see. And so you mentioned that there's kinds of almost two branches. There's like the observational side and the theoretical side. Would you say you're one rather than the other, or do you do both?
So I think I am an observer because I mostly use telescopes, and then I have observational data, and then I analyze the data. But this is the first one step. This is the measurement step. And in order to try to give a physical interpretation of the observation, theoretical models are necessary. And so I work very closely with theorists in order to develop together theoretical models to compare with the observation. So it's, I think for me, it's an exchange, and it's a collaborative work.
Yeah, I think that's like, when I think of astrophysics, I'm thinking of like huge sort of international collaborations. So you work with kind of multiple telescopes around the world, and then also in the sky. So can you describe kind of what your day-to-day life is, kind of when you're doing these experiments or observations?
Yeah, so my day-to-day life is very, how to say, every day it's different. Because I think the research that I do has different parts. So let's say the observation, which is data analysis in order to get results. So if I have, for example, an idea of doing some observation and to address a particular question, I can do the observations for a week or so, and then have data, and then I can work on this data for 6 months or years to have one publication, and after that I can still come back and work again on that. So this is one part. I don't spend my time in the telescope room doing observations. So that's why I can do...
Locked away at night, like
yes.
looking at the stars.
I mean, sometimes, yeah, but not always. So that's why I can do my research here. I don't have a telescope in my office. And so to do the observation, either I go to the observatory and do the observation myself, or depending on the observatory, the observations are done by operators at the telescope, and then they send us the data. And then there is the time to actually analyze the data. So this is writing codes in the computer and then doing data analysis. And then there is the step of discussing with collaborators. And so my day is, I do a little bit of data analysis. I think about the results I have meetings with collaborators to discuss about this. And then when we have a new result, then there is a step of writing publication, which is also an important step in research. And then there is the other step of thinking about the next project, the next observations. So for that also we need to write observing proposals so that we earn the time, observing time on these international telescopes, which are very competitive. I mean, all the astronomers want to use those telescopes, and there is not enough time for all the projects. So we need to convince the committee that our project is very important, and then we will get important results. And so we need to write a convincing proposal. And it takes quite a lot of time to do that.
Yeah, so thinking about these sort of logistical challenges, what would you say is sort of the biggest challenge in your field as an astrophysicist?
Challenge in terms of research.
Yes.
So how do I do research?
Is it this sort of competing for the time? Is it, you know, funding?
Yeah. So I think so to do research, what do we need? First, we need an idea, right? We need to know what is the big question we want to answer, and what is the new question that we want to answer. And second, what we need is data. So we need to have access to telescopes in order to observe new regions to address a new question. And then third, we need time. So we have all this data. I need time to analyze them and then get results, write papers. And then I think for me, now the most challenging part is the third one, is to get enough time to address all the different ideas that I want to answer, and then to analyze all the data that I managed to get from telescopes.
So it's actually the opposite problem. You have so much data and so little time.
I think so, yes, yeah. I mean, I want to do so many stuff, so many things, but I mean, working on the data, it's not easy. I mean, it takes time, especially if there are new data. We need to understand the data. We have to come up with a new analysis method in order to address the new question I have. And so, yeah, I mean, for me, the challenging part is time. And so either I duplicate myself to try to address all the different questions, or I try to work with, let's say, students, postdocs, who with their training, they can I work on my data and then, yeah, help me make progress in different fronts. So I think for me that's, yeah, the time issue is a problem. And in order to have, let's say, postdocs and students, we need budget. And so I would love to have more budget, to have more people working with me.
It always comes down to the budget.
Yeah.
Do you have any students that you're working with right now?
Yeah, I do have students, and also I have one postdoc here working with me. So I'm not working alone, so I have some help, but I think I want more help.
I see. So yeah, kind of thinking about your research, I'm wondering, like, what do you think is the most surprising or interesting thing that you've discovered so far?
Yeah, so I think one surprising and important result came out from my PhD work, actually. So when I started my PhD, we had new data from a space telescope, which is called Herschel. And this telescope observed the sky in submillimeter wavelengths, so which is the wavelengths where the dust in the interstellar medium emit radiation. And so this telescope was very sensitive and was able to resolve the structure of the interstellar medium. And then it revealed that the interstellar medium is full of filaments. So filaments are this kind of elongated structure from gas and dust, which came out actually to be the main site of star formation. So before I started my PhD and before we had these images, as I said in the beginning, stars form in clouds, which were described as mostly spherical. And then in these spherical clouds, the densest region, they fragment and collapse and form stars. But what these images showed is that these clouds are not spherical, they are elongated, filamentary. And then the stars form within this filament, within this filament. And so this was a really important turning point in our understanding of the star formation process. And so when I started my PhD, we had this data, and then we saw this connection between the filamentary structure and star formation. And so then I wanted to understand the properties of these filaments. And so I analyzed in detail these filaments in different regions, in star-forming region in our galaxy. And then it turned out that these filaments, they all have the same width. So they have different lengths, different masses, different densities, but they have all the same width. And then this was a very surprising result. And then, yeah, all the community was surprised, and then all the theorists were really on edge. What does this mean? And then how can we explain this?
So did anyone come up with any explanations for this yet?
Yeah, so observationally, we proposed some suggestions. One of it is that so this particular width of filaments may correspond to the scale where the properties of the cloud, the turbulent properties of cloud changes. And these filaments, they form from compression, and then this compression create this kind of filaments with a particular width. And so this is for, let's say, low density filament. But the surprising thing is that much more massive filaments, they also have the same width, and in principle, these filaments should collapse because gravity is very important, they should collapse. And they don't collapse because they accrete material. And then this accretion of material make them actually stay at that width, observed width. So this is observationally what we suggested. And then for years and years, theorists tried to explain this theoretically and from simulation. And then it was not possible until very recently, actually. The publication is from 2025, this year. So it's a young postdoc from Japan who did some numerical simulation, including new physics, and then showed that actually he could kind of explain generation of turbulence within the filament due to accretion. And so it seems that, yeah, that's one possibility that he was able to show in the simulation. But in the simulation also, after a certain time, the filament collapses.
So not quite that.
Yeah, exactly. So it's almost there, but there is still something missing. So we have to work on that.
I see. For you, is that a kind of holy grail or specific goal that you have with your research that you most want to find out?
Well, as I said in the beginning, it's star formation in general, and then understanding how star formation impact planet formation and the origin of life, and also how star formation impact the interstellar medium, the enrichment of the interstellar medium, and the evolution of galaxies. So there are some big questions in star formation. One of them is the origin of the mass of stars, as I mentioned. The other one is the efficiency of star formation. So if we look at the mass of the cloud, the mass of dust and gas, and then we measure the mass of stars, we see that only a small fraction of the available material is in stars. And the question is why? Why you don't form more stars? And so this is also one of the important debate in the star formation community. And so what is usually explained is that when you form these stars, some of them are very massive, as I said, and then they will explode in supernova. And when they explode in supernova, they actually disperse the cloud, the surrounding cloud, and then they quench star formation. This explosion quenches star formation. So some theorists think that propose this as the origin of the low efficiency of star formation. But we have a different idea, which is linked to filaments. So when we observe the mass of the fragments in the filaments that will form stars, we see that a small fraction, actually 15% of the total mass of the filament is in cores. And so the question is why? And so now we are trying to investigate why there is this small fraction of the mass of the filament which is in cores, and also what disperses the filaments or breaks the filaments. And so I think the question is a bit shifted onto the properties of filaments, and then we have maybe a more direct target.
So you have to kind of go back. It's like, why planets, why stars, you know, how do planets form, how do stars form, how do filaments form, kind of everything kind of goes back.
Yeah, and I think that, I mean, saying whether there is any holy grail or not in this field, I think in research in general, each time we have an objective and then we get closer to it and then we address it somehow, we realize actually that there is a plethora of other questions we need to address.
Yeah, it opens up like a Pandora's box of more and more questions.
Exactly.
Yeah.
And I think that's the beauty of research, is that until we get there, we cannot imagine what are the questions, what are the new questions we want to, we will have to address.
We don't know what we don't know.
Yeah, exactly. Yeah, and in research, it's the path of acquiring knowledge, understanding, making progress, having new questions.
It seems like that's what really kind of excites you.
I think so. Yeah. I mean, it's as soon as I understand something, I feel so happy, and then I realize that it's very exciting because there are so many other things that I didn't think I don't know.
Yeah.
Yeah, and then I can try to address those questions.
So as a kid, I'm wondering, did you kind of know that you always wanted to be a scientist? You seem to have this sort of insatiable curiosity for uncovering and discovering things.
Yeah, I think as a kid I was very curious, and then I was asking questions and I was trying to understand things. But I don't think I didn't know that there is this profession of doing research. I mean, as a kid I didn't know. Actually, what I wanted to be is to work with animals. I wanted to go to Africa and save the lions and monkeys from being extinct.
Yeah, I think I wanted to do that too at one point. Or to be a vet or something.
Yes, yeah. That's what because I like very much nature as well, so I like the beauty of nature on the earth, and including animals and plants. So yeah, I didn't think that I will be sitting in an office
in Japan,
doing some data analysis.
Was there like a particular moment where your kind of trajectory turned towards science and astrophysics?
I think, so I think there are different epochs which make me do what I doing today. So first of all, I couldn't do that because in the country where I was, there was no courses for that at the university, and so I needed to choose something else, and then I chose physics because I think physics, I found beautiful that with physics and mathematics we can explain things that happens around us, and then I wanted to learn more about that, and so I decided to do physics at the university. And then at some point when I was doing, at the end of my undergrad, I was invited to join a team doing observations in one of the big telescopes in Chile. And so, I got the chance as an undergrad to go there and then spent 1 week on the top of the mountains at 2,000, 3,000 meter altitude. It's an observatory called ASIA. And then during these observations, I really learned a bit the research process, so that we want to address this question, we want to do these observations, and then we analyze the observation to try to see whether we need to observe more or less, and then change the observing plan. I really enjoyed this process, and so I thought that if one day I do astrophysics, then I want to be more in the observational part, because I find it fascinating that we have this big telescope on Earth, and then we can observe things that we cannot see with our eyes, and then we can try to understand things that are far away and then not accessible, and then explain things that are so tangible to us. I mean, what is a star, what is a planet, and then how all of these form and evolve. I think this chance that I had to go and do this observation at this time gave me a hint of what is research in astrophysics. And then the topic of star formation, I think it's because it's very much linked to us.
I see. What kind of advice would you give any kind of physicists, like undergraduates, who are kind of considering a similar career to yours, to kind of advancing into astrophysics?
I mean, astrophysics or research in general, I think for me it's a wonderful profession, but it's also, it could be difficult. And so there are, I think, a few important characteristics that someone needs to have so that they could enjoy doing research. And the first of it is to be curious. I mean, to do research, you need to be curious to understand things. If you are not curious, you can not enjoy the process. And second thing is to be ready to think outside the box. So in order to make a discovery, you need to try something that was never tried. So you need to take risk. And so you need to have this will of trying something different.
And being, I guess, prepared to fail multiple times.
Exactly. We have to try many things, and then at the end we find the solution. So that brings me to the maybe third important point, which is challenge. You have to challenge yourself, and then you shouldn't give up if it doesn't work from the first time. And I think if you have these three characteristics, I think, and you are interested in the topic of topic of astrophysics. Otherwise, you can do any other kind of research. It's the same thing. I think, it's a wonderful place to be. I mean, for me, this is. I'm very grateful that I can have a salary and live from this. But for me, I don't consider it as a job. It's part of my life to do.
It's your passion.
Research. Yeah, I think so.
The kind of moving on a little bit. So you did your Ph.D. in France, and then you kind of did some postdocs in France and I think Portugal.
Yes.
What was it that first sort of attracted you to come all the way to Japan?
I think there are two equally important points. One of them is that, I spent a lot of time in, let's say, Europe and around Europe, and I wanted to experience culture in East Asia. And then I chose Japan because, so when I was a kid, I used to watch Japanese movies, so not anime, but Japanese old movies, black and white movies. And I liked very much the environment in those movies, so Ozu movies. And then, so yeah, I was curious about the country which created those kind of movies. And so Japan was, a country I wanted to visit at least. And then during my research and being at conferences, I met a professor in Japan, Japanese professor. And then I liked very much my interaction with him. So he's a professor in Nagoya University. And so then during one of the conference, I met him and I said, I would be interested to come to Japan. Do you have a position for me? He said, yeah, I have a position for you, but I think it's better if you apply for a fellowship. And so that's how I applied for JSPS fellowship, and then I came for the first time in Japan 10 years ago, in Nagoya University. And then that professor is a theorist. And so for me, it was the first time to really work with theories and understand theoretical models, understand the language that theorists use. And then, we had a very good exchange, and he's still one of my collaborators, of course.
What do you think is sort of the biggest difference between research environment in like Europe compared to in Japan?
So I think for me, I have similar kind of interactions with my collaborators. But I think that in Europe, there is a little bit more freedom in research, in the sense that researchers and also students, they don't have any obligations to be at the office from a given hour to another given hour, and then it's more flexible. In Japan, I feel that people feel more obligated or are obligated to be at the universities during working days, and so the life-work balance I find it a bit different compared between Europe and Japan. So
you hear that scientists work long hours in Japan, I think.
Yeah, and also something that I miss being here is the free time we had to discuss with researchers. So in Europe, and that's the case in France, Portugal, or many places, there is the culture of having coffee breaks, tea breaks, and have a space where researchers working on different fields can come and then have informal discussions on their research. And this is something I've never seen in Japan, unfortunately.
Yeah, it's not so common, definitely. Something to suggest to the department heads. Yeah, that's really something I miss. I mean, there are so many new ideas and new collaborations that could be created if there is a space where people can, there is a space and there is a culture where people can come, meet, discuss. I agree. One thing I am curious about then is, so you started off in Nagoya and you've been to a few other institutes in Japan. What was it that brought you to Kyushu University?
So first I didn't know very well Kyushu, so I wanted to discover Kyushu. But then it's the position. It's the position in which I am now, which is mostly a research-only position. So it's a position where I can dedicate most of my time to research. And so I think this is really I feel very honored that I have such a position where I can really dedicate most of my time to research. And also I have research fund to go to conferences, go to observatory to do my observations, and also I have some budget to hire a postdoc. And so I think this package position, it's really ideal for someone like me who really want to do research, because most of the positions in Kyushu University and also in other universities in Japan and also abroad, there are faculty positions where the faculty needs to teach, so sometimes they have heavy load for teaching, and then during the time where they don't teach, they can do research. And then for some of my colleagues, that's really very difficult to manage the time and make progress in doing research. So earlier I was complaining that I don't have enough time, but actually I don't have the right to complain because I can use all of my time to do research, and still I'm complaining. But I think,
we always want more time.
Yes, as I always want more data. But I think this position really attracted me, and I feel very grateful that I was able I am able to have this position and be here to do my research.
So this position, this is part of the Inamori Frontier Program, right?
Yes, it's part of the Inamori Frontier Program, which is run by the Institute for Advanced Study. And the aim of this program is to provide the best work condition for researchers to make their research and make progress in their research.
Yeah, great initiative. So I think probably it's time to start wrapping up. So I have a couple of kind of closing philosophical kind of questions. So my first one for you is, what do you find the most kind of beautiful or humbling thing about studying the universe?
Yeah, I mean, it's so in my day-to-day life when I work on star formation, I don't think about this, but very often, I step back and then I think about the fact that I am a human with I've lived, I don't know, a few years, and then I am talking and trying to understand things which are billions of years old, and then it reminds me that what is my place and place of humanity in the universe, and then it reminds me how beautiful is all of these things, and that we have to try to preserve as much as possible the beautiful earth on which we live.
I agree. So, my final question that I'm curious about. So when you look at the night sky now and you see all the stars, kind of the average person would just, be able to just appreciate them. But as a scientist, when you look at the stars, do you see them the same way?
Yes, yeah. I think the first thing that struck me is that the sky is beautiful.
Yeah.
So I think I still enjoy nature with my first sense, the five senses. And sometimes, from time to time, I think about it, that this is the region that I observed with the telescope, and then I know what is that. But I still see everything as I first saw when I was a kid. I think it's, first of all, it's very beautiful. And then we can try to explain it.
To understand it.
Yeah.
Yeah. All right, thank you so much for joining us today here on Science Salon. It's been a real pleasure talking to you. And thank you also for joining us. Great.
Thank you.
Thank you very much.